Hello everyone, myself Dr. Ranjith Kumar Gatla, working as an associate professor in Electrical and Electronics Engineering department. In today's class, we are going to discuss about Kirchhoff's laws, which is one of the basic law of the electrical circuits, and as well as the source transformation techniques. So before going to discuss about the Kirchhoff's laws, let me give you an idea about some basic terminologies, which are what is node, what is branch, and what is loop. So if you will able to understand what is node and what is branch and what is loop, then it is very easy to understand the Kirchhoff's laws. Okay. So as we know, a network is a interconnection of elements or devices. Okay. Then, and also this circuit or network will provide one or more closed paths. So for our understanding purpose, let us consider here one electrical circuit, and in this electrical circuit, what is mean by branch? Here, the branch represents a single element such as voltage source or the current source. So here for this particular electrical circuit, how many branches are there? So here, this is one element, the voltage source, so this is one branch, and this is the another branch, second branch, and this is the third branch, and this is the fourth branch. So this particular network or circuit consisting of 4 branches. So the branch represents a single element, okay, which is either active element or the passive element. So the active elements are voltage and current sources, and the passive elements are resistors, inductors, or the capacitors. Then next thing is, what is node? So here node is nothing but here it is a point of connection of 2 or more branches. So here, as we know, this is one branch and this is another branch, and here these 2 branches are connected at a particular point. So this is node 1. And again here, as you can see, these 5 ohms branch and 6 ohms branch and 2 amperes branch, these 3 are connected at this particular point. So here this point and this points represent same. So let us consider this is node 2, because in between these 2 points there is no element, so that's why we cannot say this is also a branch. Okay, so from here to here this is a branch. So that's why here especially, so this is node 2. And when coming to the node 3, here as you can see another point, this point, for this particular point, these 10 ohms and 6 ohms and these 2 amperes are connected at this particular point. So these 3 branches are connected at a point. So this is the node 3. So this is how we should identify the nodes and as well as the branches. And the next one is the loop. So loop is nothing but any closed path in a circuit. So here there are 2 loops. This is loop 1, let us consider, and this is the loop 2, because here there are 2 closed loops are there, or closed paths are there. So that's why, so this circuit consisting of 2 loops. So which means for this particular circuit, how many branches are there for this particular circuit? 1, 2, 3, 4 branches are there. And how many nodes are there for this particular circuit? 1, 2, 3 nodes are there. And how many loops are there? Here the 2 loops are there. Like this we should identify the branch, node and loop. So I hope everybody is clear about what is branch, what is node and what is loop. Then we will go to the actual topic, which is the Kirchhoff's laws. So these laws are defined by a scientist called Kirchhoff in 1845, and he describes a relation between the current and the voltages inside the circuit. Okay, so he described the relation between the currents and voltages within the circuit. Okay, and that relation is the Kirchhoff's laws. And there are mainly 2 different types of Kirchhoff's laws are there: Kirchhoff's first law and then Kirchhoff's second law. So Kirchhoff's first law is associated with the currents flowing through the circuit, and Kirchhoff's voltage law, the Kirchhoff's second law is associated with the voltages present in the circuit. So that's why the Kirchhoff's first law is also called as Kirchhoff's current law, and the Kirchhoff's second law is also called as the Kirchhoff's voltage law. So the most popularly we usually differentiate the 2 Kirchhoff's laws are Kirchhoff's current law and Kirchhoff's voltage law. Okay, in simply we can call it as KCL and KVL. Right. Then first let us discuss about the Kirchhoff's first law, which is the KCL. Okay. So according to the Kirchhoff's first law, or according to the Kirchhoff's current law, it states that the algebraic sum of all the currents entering and leaving at a node must be equal to 0. Okay, so it states that the algebraic sum of the currents entering and leaving at a node is equal to 0. Or in other words, the sum of the currents entering towards the node is equal to sum of the currents leaving from the node. So these are the statements according to the Kirchhoff's current law. So which means, let us consider here a node, and this particular node having different branches, and there is a current flowing through each branch. Let us consider here, this is the direction of the current I1, and this is I2, and this is I3, and this is I4. So according to Kirchhoff's law, the algebraic sum of the currents entering and leaving the node equal to 0. So here what are the currents entering to the node? Here I1 is current towards the node and I2 is also current towards the node. So I1 plus I2, and I3 is current leaving from the node, so opposite. So that's why here it is I3 minus I3, and again I4 is the current entering towards the node, so I4, which is equal to 0. So here, because we are taking the reference direction of the current is the current towards the node, so that's why we have given the positive sign for that one. And then automatically, if the current is opposite to our reference direction, then that is the negative sign. Or in other words, the sum of the currents entering towards the node is equal to the sum of the currents leaving from the node. So which means the entering currents are I1 plus I2 plus I4, which is equal to the leaving current is I3. So this is the Kirchhoff's first law, which is also called as Kirchhoff's current law. Then next one is so here let us consider a circuit, and in the circuit here let us consider there are different resistors are there, and the different current is flowing through the different branches. So here the current flowing through the R1 resistor is, let us consider IR1, and the current flowing through the R2 resistor is IR2, and the current flowing through the R3 is IR3, and similarly IR4, IR5 and IR6. Okay, so let us consider here this is a node, and at this particular node we should apply the Kirchhoff's current law. So according to the Kirchhoff's current law, the sum of the currents entering towards the node is equal to sum of the currents leaving from the node. So what are the currents entering towards this node? Here I4 is current towards the node, and IR1 is also current towards the node. Okay, but here IR5 and IR3 and IR2 are currents leaving from the node. So which means IR4 plus IR1 is equal to IR2 plus IR3 plus IR5. So that you can see IR1 plus IR4 minus IR2 minus IR3 minus IR5 is equal to 0. Because here we are considering the current towards the node is a reference current direction. So that's why if the current is leaving from the node, then that is the opposite direction of our reference direction. So that's why we have assigned the negative sign. Okay. Or in other words, IR1 plus IR4, which is the currents entering towards the node, is equal to IR2 plus IR3 plus IR5, which are the currents leaving from the node. Okay, so this is how we can apply the the Kirchhoff's current law. Then coming to the Kirchhoff's second law, which is Kirchhoff's voltage law. So according to the Kirchhoff's voltage law, in any closed loop network, the total voltage around the closed loop is equal to 0. Okay, so the total voltages around the loop is equal to 0. Okay, or in other words, the algebraic sum of all voltages within the loop is equal to 0. So which means, again, let us consider a circuit. Okay, so here let us consider the voltage across the R1 is, the source voltage is Vs, and let us consider the voltage across the R1 is VR1, and voltage across the R2 is VR2, and the voltage across the R3 is VR3. So which means, according to the KVL, the total voltage around the closed loop is equal to the sum of the all voltage drops within the same loop. So which means here Vs is the total voltage around the loop, which is equal to the sum of the voltages drops across the loop. So what are the other voltages drops? VR1, plus VR2 plus VR3. Okay, or in another words, okay, so Vs minus VR1 minus VR2 minus VR3 equal to 0. So this is how we can apply the Kirchhoff's voltage law. Here, by using this Kirchhoff's current law, okay, by using this Kirchhoff's current law, find what is the current flowing through the resistor R6. What is the current flowing through the resistor R6? So just apply the Kirchhoff's current law at this particular node. Already we have applied. So then the equation is IR1 plus IR4 minus IR2 minus IR3 minus IR5 is equal to 0. And similarly apply the, what is here IR1, IR4 and substitute here IR1 is equal to 5 amperes and IR4 is equal to also 5 amperes and IR5 is equal to 2 amperes and here IR2 is equal to also 5 amperes. If you substitute, then you will get IR3. So here IR3 is equal to 3 amperes. Then next is apply the Kirchhoff's current law at this particular node. So IR3 is the entering current and IR5 is entering current, but IR6 is the leaving current. So that's why IR3 plus IR5 minus IR6 is equal to 0. Then substitute here IR3 values and IR5 value also we know 2 amperes. Then you can find IR6. Okay. Then IR6 is equal to 5 amperes. So this is how we can find the current flowing through any resistor by using these Kirchhoff's laws. So that's why these are also called as a basic network reduction techniques. These Kirchhoff's laws are also called as a basic network reduction techniques. Fine. So next, by using same Kirchhoff's voltage law, okay, find what is the voltage across the resistor R3, which is VR3. Again, same way here, as you know, Vs is equal to what is that VR1 plus VR2 plus VR3. Then substitute all these values because we know what is Vs value and what is VR1 and what is VR2. Then we can find VR3 value. Okay. So in this equation, if you substitute all the values, then you will get VR3 is equal to 5 volts. So in this way, by using Kirchhoff's voltage law, we can able to find the voltage across any other element. So which means by using these Kirchhoff's laws, we can find the voltage across any element or the current flowing through the any element. Okay, so this is how the Kirchhoff's laws, Kirchhoff's first law and the second law. Okay, then next topic is source transformation. This is also a one kind of network reduction technique. So source transformation, which because what are the different sources that are available? One is current source, another one is the voltage source. So the source transformation is nothing but voltage source to current source and current source to voltage source. So how we can transfer the voltage source into, or how we can represent the voltage source in terms of the current source and how we can represent the current source in terms of the voltage source, that we are going to discuss here. So further here, first before that, let us discuss about the voltage division rule and as well as the current division rule. So first, the voltage division rule. Okay. So here the voltage divider circuit are useful in providing the different voltage levels from the common supply voltage. Okay. Then how the voltage division rule can be applied? Which means, let us consider here this is the total voltage Vs. Okay. Then let us consider the current flowing through the circuit is I. Okay. Then how to find the voltage across R1 and R2 and R3? Because the total voltage is divided, okay, into the total voltage is distributed, some of the voltage across the R1 and some of the voltage across the R2 and some of the voltage across the R3. Because as we know, according to the KVL, here Vs is equal to VR1 plus VR2 plus VR3. So which means this total voltage is distributed across the various resistors which are connected in series with that particular voltage source. Then how to find this VR1 and how to find this VR2 and how to find this VR3, because this total voltage is divided into three different voltages. One is VR1 and one is VR2 and one is VR3. That is the voltage division. Then how to find? So first let us find the total current I. I is equal to Vs by R1 plus R2 plus R3, because I is equal to V by R. Here R is the total resistance and these three resistors are connected in series. So that's why here the equivalent resistance is R1 plus R2 plus R3, so that we can get Vs by R2. Then suppose if you want to find the voltage across VR1, I into R1, so again I is equal to Vs by R into R1, so then VR1 is equal to Vs into R1 by RT. So Vs into R1 by the total resistance RT. Even we no need to know about the current. If we don't, without knowing the current also, we can find the voltage across, how the voltage is divided across the various elements. Similarly, if you want to find VR2, then here R2 by RT into Vs, and similarly VR3 is equal to R3 by RT into Vs. So in this way, we can find the voltage across the various elements which are connected in series with the main source by using the voltage division rule. So by using the voltage division rule, we can find VR1, VR2 and VR3. Next, the current division. In a common way, we can write Vn is equal to Vs by Rt into Rn. So here Rn is which resistance, whether it is across first resistance, second resistance or the third resistance. And here Rn, Rt is the total resistance across the circuit. Then coming to the current division rule, because if it is a current division rule, because as you know, this is the total current I, this total current I is dividing into I1 plus I2. So that's why this particular node, according to the Kirchhoff's current law, I is equal to I1 plus I2. So which means this total circuit current is dividing into two different resistors. So then how to find the current flowing through the R1 and how to find the current flowing through the R2. So which means how the total current is divided into these two currents, I1 and I2, that we are going to find. Okay. So for that here, because as we know, the voltage across the parallel elements is same, which means the voltage across R1 is Vs and the voltage across the R2 is also Vs. Right. So let us consider here, this is the total source current Is and the current flowing through the current resistor R1 is equal to IR1 and the current flowing through the resistor R2 is equal to IR2. Then here IR1 is equal to, because the voltage across the resistor R1 is equal to, Vs by R1, and here R2 is equal to Vs by R2, and Is is equal to Vs by the total resistor across these two elements is RT. Here RT is equal to, what is R1 R2 by R1 plus R2. Then suppose if you apply the Kirchhoff's current law, Is is equal to IR1 plus I2, then substitute these values, then you will get IR1 is equal to, here Vs, so then what is that, Is, into RT by R1, if you simplify. Similarly, if you substitute all these values, then IR1 is equal to Is into R2 by R1 plus R2. The same way, if you want to find IR2 is equal to Is into, R1 by R1 plus R2, which means, if you want to find the current flowing through the R1, then the total current Is into the opposite resistance R2 by the total resistance. And similarly, if you want to find the current flowing through the R2, then total current Is into the opposite resistance R1 by the sum of the two resistors R1 plus R2. This is how we can find these IR1 and how the current is divided across the circuit. Or in common way, we can write IRN is equal to Is into R opposite by Rn plus R opposite. So R opposite is the opposite resistance. Here Rn is, so through what resistance you want to find the current, and ROB is again the opposite resistance. So I hope everybody is clear about how we can apply the current division rule and voltage division rule. So the voltage division rule can be applicable when the elements are connected in series, and the current division rule can be applicable when the elements is connected in parallel. Why? Because when the elements are connected in series, the current flowing through the circuit is same. So that's why there is no current division, because here let us see, the current flowing through the R1 is I, and current flowing through the R2 is also I, and current flowing through the R3 is also I. So there is no division here. Because the current flowing through the circuit is same, because all the elements are connected in series. Similarly here, if the elements are connected in parallel, then the voltage across each element is same, which means the voltage across R1 is equal to Vs and voltage across R2 is equal to also Vs. So that's why there is no concept of division of the voltages. So that's why, in series, the voltage division, and in parallel, the current division. Then next concept is the source transformation. So how we can transform, one kind of source, which means voltage source to current source or current source to voltage source. So this is possible only the practical sources. Okay, and independent practical sources, not dependent. Independent practical sources, which means independent current source or independent voltage source. So independent practical current source can be converted into independent practical voltage source, and as well as the independent practical voltage source can be converted into independent, okay, practical current source. Okay, then how we can convert? So if you want to convert the voltage source into current source, it must be a practical. Okay, the practical means the practical current voltage source is nothing but, okay, so there is an internal resistance in series, there is an internal resistance connected in series with that particular voltage source, then it is a practical current, practical voltage source. So then this practical voltage source is converted into practical current source. So in that case, just we are replacing this voltage source as a current source, and we are replacing the series connected resistance as a parallel connected resistance for that particular current source. So which means here this voltage source is replaced as a current source, and the same resistance here we are connecting in parallel with the current source. Okay, and the value of the resistance, whatever the value of the resistance here is, we are replacing the same resistance value here. Then what about the IS? Because as you know, IS is equal to VS by R. Okay, so here what is that? Here RL is equal to VS by IRL. Okay, so in that way we can, because IS is equal to, here IS is equal to VS by RS. Then you can replace this IS. Then same way we can also transform this current source into voltage source. So for that here, just from here to here. So this current source is replaced by the voltage source, and this parallel connected resistor is connected in series. Then what is Vs is equal to, V is equal to Is into Rp. So here Rs and Rp are same. Rs is equal to Rp. The same value we have to replace. So this is the source transformation technique. The voltage source to current source and current source to voltage source. Okay, both way it is possible. So if you want to convert the voltage source into current source, then you must have a series resistors, a resistor which is connected in series with the voltage source. And if you want to convert the current source into voltage source, then you must have a resistor which is connected in parallel with the current source. Then only, because this combination is called as a practical voltage source and this combination is called as a practical current source. So that's why, as I mentioned, only the practical voltage and current source can be transformed from voltage to current source and current to voltage source. Okay, then here let us discuss about one problem. Okay, how to find the voltage sources into current source and current sources into voltage source. Because this is also, as I told you, one kind of network reduction technique. Okay, so by using this network reduction technique, we can able to find again the current flowing through any network or the voltage across any network or any element. The current flowing through any element or the voltage across any element. So in next class, we will discuss about how to find the equivalent values of the series and parallel combination of the elements. So which means if the two resistors are connected in series, then what is the equivalent resistance? And if the two inductors are connected in series, then what is the equivalent inductance across those two terminals? And if the two capacitors are connected in series, okay, and what is the equivalent capacitance across these two terminals? Not only in series, even the parallel also. And before that, we should also know how to identify whether the two elements are connected in series or parallel. That also we will discuss in the next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.